Hello. So we learned how to compute the weighting matrix, optimal weighting matrix, and how to compute the variance, asymptotic variance. And the most common application of the GMM method is to the instrumental variable linear regression model. So the standard IV regression model and the moment condition is given by this. So Z, the instrument Z, is uncorrelated with epsilon. So you may put you may put y minus x beta, but I write the other way because the derivative with respect to beta is positive when you write it this way. So multiplying -1 does not matter because anyhow it will be equal to 0. So Z times epsilon should be 0. And epsilon it equals to epsilon when beta equals to the true parameter beta. As I said, I multiplied negative sign, and then the derivative is simple, zx prime, and I will verify the consistency and asymptotic normality and derive the asymptotic variance and then weighting matrix. It's simple. I will skip this. You can just read through. There is nothing much to explain what it is. So what we need here is read what assumption we used here for this to be a unique answer to this equation. The rank must be k, and theta is compact. The parameter space must be compact, and G must be continuous and bounded. The boundedness is also okay, and W is strictly positive definite and consistent. So nothing special at all. The asymptotic normality is a little more involved, but it's still pretty simple. The derivative is simple. The rank of G, the rank of the derivative must be K, which is required by the identification conditions, and omega is the variance, and trivial. So then you have this complicated variance formula. Just plug in the G, W, G, omega, and remember, G was given by this and omega was given by this. If you assume that epsilon is homoscedastic, if epsilon was homoscedastic, omega can be simplified to this, and sigma ZZ is so expectation ZZ prime is written as ZZ, expectation ZX prime is written as sigma ZX. Then the asymptotic variance is written this way. And later we are so earlier we learned the weak instrument problem. The instrument was weak if the covariance is close to 0. In this case, the weak instrument is captured by this guy. So if this is close to 0, so remember, there are 6 things are close to 0. This is 0, this is 0, this is 0, this is 0. No. This is 0, this is 0, this is 0. So 4 of them are denominator and only 2 of them are in the numerator. So when it converges to 0, the denominator goes to 0 faster. Therefore, the asymptotic variance will converge to infinity. So the weak instruments may cause some problem. Okay, it's a connection to the older one. And plug-in estimators. Also, estimators are easier in this case because the derivative does not depend on the parameter. So you don't need to calculate anything for G hat. But when you calculate sigma squared, the variance of epsilon is obtained by beta hat. So obtained as y minus x beta hat. So you are using your estimator after you obtain the estimator, calculate the variance of epsilon. Okay, and in this case, what is the optimal weighting matrix? Optimal weighting matrix is its inverse. So omega inverse, remember omega was sigma squared times expected value of z prime. Z prime is not a problem, but we do not have sigma squared because sigma squared is dependent on beta. So you need to know epsilon, and to know epsilon you need to know beta, but we cannot use any beta when we calculate the optimal weighting matrix. So when I asked like last year in the homework or in the exam, I made this as a question: what is the optimal weighting matrix? First, wrong answer is how would you use, what kind of weighting matrix are you going to use? A wrong answer is this. This is not available. So the sigma itself is not available. You have to discuss how to estimate this. Also, you have to discuss 1 over sigma squared. You have to discuss how to estimate that. That's implementation. And that's the worst. That is a wrong answer. And second best answer is that you can use the identity matrix to estimate some kind of consistent beta first. And then using beta tilde, the first stage beta, estimate sigma tilde squared. So that is an estimator of sigma squared, and you plug that into here, and this part is easy to handle by this. So that could be your weighting matrix. That is the second best answer. But the first best answer is that sigma squared does not matter because it does not depend on, it is one-dimensional. So multiplying theta squared, like sigma squared or not, does not change your maximization problem. So does not change your minimization problem at all. So multiplying 2 or not does not change the result. So the correct answer is that you don't need to care about this. So forget about sigma squared. Multiplied constant does not matter in the minimization problem. Therefore, in practice, you may use this weighting matrix. Weighting matrix would not depend on sigma squared, so you don't need to use the first step estimator at all. First step estimator is not needed at all. Just calculate z prime average. So then you are going to get this average, this asymptotic variance. The asymptotic variance need be estimated again, and here then you need to estimate sigma squared, but that is not a problem now because you already calculated beta hat using the optimal weighting matrix. So it's not a big problem. And this is an interesting example because the optimal weighting matrix does not require the knowledge of the true parameter. So without knowing the true parameter, you can approximate the optimal weighting matrix. Therefore, you don't need two-stage GMM. That's a result. And we are going to think about this asymptotic variance, where it came from. So Z is n by m matrix. So all the data is stacked within this matrix notation. So think about this as matrix. Sample size n by number of instruments m, n by m, n by m, n by k. So they are estimators. And then you may rewrite the variance estimator in this way. So zx, zz, it looks like familiar. It looks pretty familiar, and in the middle is the projection matrix onto z, right? Do you remember? It is the linear projection matrix. So you may interpret the variance matrix estimator in this way, right? So if you define x tilde as the projection of x onto z, so define this much as x tilde. And remember, the projection matrix is idempotent, so you can multiply. So pz equals to pz times pz. So if you define this much as x tilde, you have this format. So compare this with the OLS variance estimator. OLS variance estimator took this form. Similar, x prime x inverse. But now you have x tilde prime x tilde inverse. The difference is x and x tilde. So you may understand the IV regression as a regression onto x tilde, which is already a linear projection of x onto z. This is exactly the two-stage least square idea. So the two-stage least square idea can be seen in here. So that's an interesting relationship. And another interesting example is to think about the scalar case to give you a better intuition. So now think about one-dimensional x and one-dimensional instrument. Then the asymptotic variance can be written in this way. So you can simplify a lot of things. And think about the correlation coefficient rho, and using the correlation coefficient, you may rewrite the asymptotic variance in this form. And remember, OLS estimator had the variance like this. So the difference here is because you are using the instrument, your variance is divided by omega squared, like rho squared. Rho squared is multiplied, but rho is smaller than 1, so divided by rho squared means your variance is amplified. So this variance will be the same as the OLS estimator if the correlation equals to 1, which means x equals to z. So that is the OLS. It is another interesting relationship to see how GMM, the instrumental variable, is related to the OLS estimator. So it is always it has always larger variance than the OLS. Excuse me, it has to be 1. I said 0, but this typo, it has to be 1. And the weak IV, the last thing I talk about. So the weak IV in the scalar case, you can understand the weak IV as rho converging to 0. The correlation between x and instrument is converging to 0, close to 0. And then obviously if this goes to 0, obviously the variance diverges to the infinity. Therefore, the weak IV causes a big problem. The standard error of the estimators will be too big. And also it makes this matrix singular. So the variance matrix, where do we have it? So this variance matrix, variance matrix, where is it? So I have to go much further. The variance matrix, this variance matrix will be non-singular and will be singular. So this matrix will be not invertible. So that means its determinant will be close to 0. So you may understand matrix inverse where the matrix determinant is close to 0 is a kind of infinity. So just conceptually, you may think the determinant going to 0. Okay, this is the GMM, and I think the midterm will cover up to this point. Next lecture, I will maybe I will review homework 2 and maybe 3 to help you prepare for the exam. And yeah, good luck with the exam. And I'll be very generous in grading. Don't worry too much about the exam. Just do your best. Try your best, and stay healthy. See you later. Bye.